So we will look at the derivative of a function. So remember, the derivative at a point A is equal to the limit as h goes to 0 of f of a plus h minus f a all over h. If you replace the a with an x, then you get the derivative as a function. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f x all over h. Then the question is this a function? And the answer is, well, yes, because a function's definition is for every input, there's only one output. And for every input you put in here, for every x you put in, you're only going to get one value out. So yes, it is a function. So therefore, all of our derivatives are also functions themselves. So we can now define the derivative of a function. It is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. The domain of this, because it's a function, it has a domain, and it's all x for which the derivative actually exists. So that will give us the idea of, does the derivative always exist? We will explore that in a little bit. But let's go ahead and look at this example here, where we have a graph of a function, and what I'd like to do is come up with the graph of the derivative. So this is actually the graph of f. And what I'd like to do is kind of figure out what the derivative is. So let's think about what we know about derivatives. Their rates of change. They're how fast is the function changing over time. So one of the things that you might notice is at this point right here, if we looked at, there's also the slope of the tangent line. So if you looked at the slope of the tangent line at this point, it's horizontal. And the slope of a horizontal line is, of course, 0. So the derivative at this point would be 0. Looking at this more closely, it kind of looks the same thing here, where if I were to draw a tangent line at this point, I would have a horizontal tangent. So at this point, we would also have 0. Now, over here, if I were to draw tangent lines, one thing I notice is this tangent line slope is negative. This tangent line slope is also negative, but not as negative. This is more negative than this is. This is also negative, but notice this one's more negative than that one. So it looks like we're very negative, we're less negative up to 0, we're still less negative, but then we're more negative. Then it looks like here, again, that tangent line would have a less slope. And then we're back to 0. So it looks like we might be doing something like we're negative, 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 coming up here to 0, coming back down, being negative, more negative, less negative, and then back up here to 0. Now let's look at these. Here, that slope's positive. Here, that slope's even more positive, which means positive means we're above the x-axis. So this means they're positive, but they're getting more positive as we go. So therefore, the derivative must be looking something like this. Getting more and more positive. So this looks like it could be the derivative. So that's a graphical interpretation of it. Let's look at a numerical interpretation. Let's say we have P of t be the percent of Americans under the age of 18 at time t. The table gives values for this function in census years from 1950 to 2000. So in 1950, 31.1% of the population was under 18. In 1980, it was only 28.0%. And in 1990, it was 25.7. But in 2000, it was only 35.7. So the values changed a little bit. Wait, actually, I think this value must be wrong. Let's change it. Let's fix this. I think this is actually still 25.7. So notice, it looks like we're getting less and less and less percent of people that are under 18. So it looks like our values are changing. It looks like something's going on with these values. And what we want to do is figure out what that is. And so we want to look at the rate of change. So remember, rate of change is just a slope. So we could actually look at the slope between these 2 points. That would be 35.7 minus 31.1 over 1960 minus 1950. Now, it's not a perfect derivative, but it gives me a good idea of what the slope is, and the slope is 0.46 here. So here we were actually increased because it's positive. It means we must be getting more. So let's look at these two. So here we'd have 34.0 minus 35.7 over 1970 minus 1960. One thing you're going to notice is 34 minus 35 is going to give you a negative answer. So this is negative 0.17. That means we must be getting less as time went on. Let's look at these two. So again, we take 28.0 minus 34.0, and we'd have 1980 minus 1970. And this looks like to be negative 0.6, or 0.6, yes. And the same thing here, we can do these. Noticing this, you can just tell when I subtract these two numbers, we're going to get 0. All right, so this gives us an idea of what they are, and one of the things you can see is the rate of change was positive, then it became negative, which means we got less and less kids, people under 18. And so that what this means is this is the rate of change of the percent of Americans under 18 every year. So this should be the meaning of P prime, sorry. And what the meaning is, and just I'm going to type it because it'd be a little faster. The meaning is that this is the rate of change of the percent of Americans under the age of 18, under 18, every year. So again, you notice it's getting smaller, it's negative, was positive, then it became negative, and even more negative. So it's actually becoming decreasing. We're actually getting a decreasing rate or negative rate. And it became 0. So now the rate's constant at that point. All right. So we constructed our values. Oh, let's figure out what the units are. What are the units? So again, your numerator is going to be percentage. Your denominator is years. So your units is equal to percent per year. We can graph these. So here I graphed them on Desmos. This is P. So these dots up here are the percent values. These dots down here, which are kind of hard to see, but these dots down here are the rate of change. And then the question could be, we could actually, if we wanted to, we could draw a graph that goes through them, so we could actually come up with a regression line that goes through all these points. You can use statistics to get a better line. We can actually do the same thing here. I'm going to pick a different color. We do the same thing here, seeing what the rate of change is doing. And you're noticing the rate of change is negative, negative, and then it goes to 0. I'm not going to draw beyond that because I don't know what happens after beyond that. I don't know if it's increasing or decreasing. So we don't know if this is increasing or decreasing because we don't have the data. The question is, how could we get a more accurate answers values for P prime? Well, you could actually do this where you could come up with the equation that came up with this. You find the function that actually came up with this value. And then from knowing that function, you can then find the derivative, the rate of change. So what we're going to do is we're going to find the derivative for a function, f of x equals x to the 4th minus 2x, and then we're going to find the domain. All right, so the derivative f prime of x, so it's a function, is the limit as h goes to 0 of f of x plus h minus f of x all over h. And that would be the limit. Again, you haven't done the limit yet, so don't lose that. And our function is x to the 4th. So we have something to the 4th minus 2 times something. And then we have that again. We have something to the 4th minus 2 times something. So all your numerator is your function minus your function. But then you got to fill in what the somethings are. In the first something, it's x plus h. In the second something, so it's x plus h here too. In the second something, it's x. All right, so now we're going to go ahead and multiply everything out. This is just algebra. So when you multiply out this, you're going to have x to the fourth plus something times x cubed times h plus something times x squared times h squared plus something times x times h cubed plus something times h to the fourth. So when you multiply x to the fourth, that's what it becomes. Then you use Pascal's triangle and you go to the fourth line with the 4 and you'd see that you'd have 1, 4, 6, 4, and 1. Minus 2x plus 2h. Then minus x to the fourth plus 2x. All over h. Don't lose the h in the bottom because you haven't dealt with it yet. We haven't done the limit yet, so don't lose it. Now collect like terms. I notice I have an x to the fourth and an x to the fourth. I notice I have a, oops, I missed something. See, this is where you see you made a mistake. So I made a mistake. I forgot my 2x minus 2h. So this is this first part, and I forgot this part. All right, so now I'm going to collect like terms again. My 2x and my 2x cancel. And I cancel my x to the fourth, sorry. I said the wrong thing. I canceled the h to the fourth by accident. All right. Okay, so now what I have is I have 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth. Again, my 2x is canceled, but I also still have that 2h. All over h. So again, what I notice is everything in the term in the numerator has an h in it, so I can fold that h out, and that will cancel that h in the bottom. So I'm going to have 4x cubed plus 6x squared h plus 4x h squared plus h to the fourth, h cubed, sorry, plus 2. Now you're going to let h go to 0. So 4x cubed has no h's in it. So it really is considered a constant for h. So it's the limit as h goes to 0, 4x cubed is just 4x cubed because there's no h there. The limit of this term, if you put 0 in for h, you're going to get 0. The limit of this term, you put 0 in, you're going to get 0. Same thing here. And then you're going to have plus 2. All right, so there was that example. That's how you find a derivative. Let's do another example. Let's find for f of x equals 1 over x, let's find the derivative. Oh, I forgot to find the domain. Let's go back and find the domain of this. So this function, since the limit always existed, didn't matter what we were doing, the derivative and this derivative always has a domain of all real numbers. The domain of this function is all real numbers. All right, now let's move on. Let's do another example. Let's find this derivative. So this is going to be the derivative. Again, the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's the limit as h goes to 0. My function is 1 over something, and I have 1 over something again. In my first something, we have x plus h. In my second something, I have x. This again, I can't figure out how to get rid of the h in this format, but it's a complex fraction. We got a fraction within a fraction. So the best thing to do is to multiply the numerator by the lowest common denominator. The lowest common denominator in this case is just going to be x plus h times x. Whatever you do to the top, you better do to the bottom. So now what I have is the limit as h goes to 0. Multiplying the x plus h times h through, the x plus h cancels in the first one, you're left with x. The x's cancel in the second one, and you're left with x plus h. In the bottom, again, I wouldn't multiply anything out. I would leave this unmultiplied because I'm going to have to factor and get rid of this h. If I multiply everything back, I'd have to get rid of it in the end. I'd have to factor again. So I'm not going to do that. Limit as h goes to 0. Collect like terms. X minus x is going to be 0. I'm going to have minus h in the top. Now I notice my h's will cancel. So I end up with the limit as h goes to 0 of minus 1 over x times x plus h. Now I can let h go to 0. So this again is the only calculus step here. So I'm going to get minus 1 on the top. X again has no h's in it, so it's considered a constant in terms of limit as h goes to 0. So x just stays as an x. X plus x again stays as an x, but x plus h is just going to be x. So you notice you get negative 1 over x squared. The domain of this function is not going to exist if x is 0. So it's from minus infinity to 0, and then from 0 to infinity. All right, let's do another one. Let's find this function, f of x equals 2 minus x over 3 plus x. Let's find f prime. So f prime of x again is the limit as h goes to 0 of f of x plus h minus f of x all over h. It helps to have this memorized, and one of the things you'll notice is I constantly write it down every time I go to use it. That helps me to memorize it. It may not help you, but I do find it helps me. So you might try that if you can't figure it out. I have 2 times something over 3 plus something. That's my function. So I have that function. And then I have that same function again, 2 minus something over 3 plus something, all over h. In the first something, it's x plus h. In the second something, it's just x. So again, I've got a complex fraction. I've got a really ugly looking stuff going on here. But the nice thing is I can just multiply by the lowest common denominator. And the lowest common denominator turns out to be 3 plus x plus h and 3 plus x multiplied together. So you just take your 2 denominators, multiply them together. That's your lowest common denominator in most cases when we're doing these. So remember, whatever you do to the top, you do to the bottom. I again would not multiply out the bottom because you're going to be factoring back again. So if you multiply it out, you're just going to be creating more work for yourself. Now go ahead, multiply this times this common denominator times the first fraction. You'll have what you have left in the numerator, 2 minus x plus h, times the 3 plus x, because the 3 plus x won't cancel. But the 3 plus x plus h does cancel. Minus 2 minus x, and then the 3 plus x cancels, but the 3 plus x plus h does not. And then your denominator is just h times 3 plus x plus h times 3 plus x. And again, don't multiply that out because you will be factoring again. In a sense, multiplying it if you're going to factor. Now, we do need to collect like terms, multiply everything out here. So we're going to have 2 times 3, which is 6. 2 times x, which is 2x. Minus x times 3, which is minus 3x. Minus x times x is minus x squared. Minus 3 times h is minus 3h. And minus h times x is minus hx. Then minus 2 times 3 is 6. 2 times x is 2x, but there's a minus sign, so minus 2x. 2 times h is 2h with a minus sign, so minus 2h. Minus x times 3 is minus 3x, but there's a negative sign, so plus 3x. Minus x times x is minus x squared, but there's a minus sign, so plus x squared. And then minus x times h is minus xh, but a minus sign, so it's positive. All over that denominator. Don't lose the denominator. Just because it's the same every single time doesn't mean you don't have to write it every time. I realize that means more writing, but it helps to keep it. It also helps to keep the limit as h goes to 0, so you don't forget to do that. All right, so now we're going to collect like terms. I notice my 6 cancels with my 6. My 2x cancels with my 2x. My 3x cancels with my 3x. My hx cancels with my xh. And my x squared cancels with my x squared. So I end up with minus 3h and minus 2h. So I end up with a minus 5h in the top over h times 3 plus x plus h times 3 plus x. Again, you can now cancel. So we'll go ahead and cancel there. So we have the limit as h goes to 0 of negative 5 in the top and 3 plus x plus h times 3 plus x in the bottom. Now we let h go to 0. Negative 5 is just a constant, so the limit is just a constant. 3 is just a constant. X is not a constant in your mind, but x is a constant in terms of my limit because my limit is involved h and not involved x. So x is actually a constant. And so it's just x. H goes to 0. And you got 3 plus x. So I end up with negative 5 over 3 plus x quantity squared. And there's your derivative.